Okay, so hopefully I'm sharing the correct screen this time, and you, if you're watching this on the video, will be able to see the slides as opposed to just the YouTube page. Okay, so we're going to be talking about nonlinear models today. After we talk about the fact that I'm an employee of Columbia University, a co-founder of Stand Group, and therefore required to disclose these facts in presentations. So just a few announcements. Once again, there's going to be review sessions tomorrow. They're identical. You can go to either one. Should not go to both. It might be a little bit hard to fit everybody into 270B, but you can go to either. One starts at 4:30 and the other goes till 5:15. The other goes from 5:15 until 6. So we'll have an opportunity there to review the syntax for calling things in rstand-arm and BRMS, passing it off to Shiny Stand, doing posterior predictive checks, all those sorts of things. I forgot to mention this on Tuesday, but Rob Trangucci, who was a QMSS student who graduated a couple of years ago, is giving a meetup talk for sort of quantitative finance, and that's going to be in Pupin Hall at 7 o'clock. So I think the QMSS students were already invited to this separately. So if you are a QMSS student, I'm sure you can go, but there's like a different sign-up process if you want to go if you're a not QMSS student. So you need to click on the meetup link. I think it's like a few dollars just to keep people from RSVPing and then not going. But anyway, Rob is going to be talking about Gaussian processes, which in a manner of speaking are similar sorts of models to what we're going to be talking about today. If you can't go, that's fine. We'll be talking about Gaussian processes in this class in a couple weeks. So be sure to already write down that URL or click. Well, I guess you can't click on this screen, but load it in your browser soon. I think there's only a few spots left for not QMSS students. If you're a QMSS student, I think you can probably just show up if you weren't already planning to. So today, we will continue to discuss the BRM function in the BRMS package, compare it to what is available in the rstand-arm package, with a special focus on estimating models that have a nonlinear relationship between the predictors and well, it's not a linear predictor, but to the conditional mean. We will have homework. It'll be posted tonight, due before class next Thursday, as usual, and it'll involve rstand-arm, BRMS, etc. Questions about that? Any of that? Okay. So we're going to be talking about nonlinear models today, and it's as good a time as any to question why linear models are so prevalent in the social science applied literature, whether that's frequentist or even the smaller Bayesian literature. But linearity is really more of a computational assumption or assumption that we might make for computational reasons, or people might make for computational reasons, rather than for substantive reasons. And by a linear model, I basically mean the sorts of models that we've been talking about so far, where the linear predictor eta is equal to, some x vector multiplied by some coefficient vector, which can be written as the sum of the products between the X variables and the predictor for that unit of observation. For generalized linear models, there's a nonlinear function relating eta to the conditional mean of the outcome for that observation. But that's not really what we're talking about. Generalized linear models are like linear models in that eta is a linear function of the predictors. And that doesn't change if we're doing a hierarchical model that we wrote in the form that we did last week, where we have, y, or in general, eta is equal to x times beta plus z times b, where z is this matrix that's constructed with, basically speaking, interaction terms between some of the predictors and some of the group level indicators that still comes out to a nonlinear model, or still comes out to a linear or generalized linear model. The same sort of thing is true with interaction terms, although those models are not linear in the X variables, and that may be something that you want to specify. They are, linear or generalized linear in the parameters. You're still just estimating, the coefficient. And so that's a multiplicative and an additive effect rather than something, nonlinear. So we'll be talking about nonlinear models today, but it's amazing how many things there are out there in the sort of applied quantitative analysis literature that, go back to the days when the only way to estimate a model like that would be to impose linearity assumptions. So like the first sort of regression model that became, widely feasible was ordinary least squares. And it wasn't until, considerably later that people could do, maximum likelihood estimation to estimate a logit model. But, during that time where ordinary least squares was feasible and maximum likelihood estimation was not feasible, ordinary least squares has an analytical solution in terms of linear algebra, whereas maximum likelihood estimate typically have to be done numerically on a computer. So there was like a few decades where, ordinary least squares was feasible, logit models, probit models were not feasible, and it became acceptable to estimate models that have, binary outcomes still using ordinary least squares, because that is what was computationally feasible, the so-called linear probability model. But there was never any reason as to why that would be a good model or something that's appropriate. You can get, predictions that are outside the 0 to 1 interval, so you can't really interpret those as probability. The error variance is not going to be, or the errors are not going to be distributed normal with constant variance, thus you're going to have heteroscedasticity. And even though ordinary least squares was producing, numbers, and those numbers, the coefficients gave sort of a linear relationship between the binary outcome and the linear predictor, the standard errors and the p-values and the confidence intervals, all those things were completely wrong. But it became sort of accepted that applied researchers could use a linear probability model just because that was the only thing that was, feasible in like 1950s, 1960s. But it took decades for it to be sort of widely recognized that estimating linear probability models was an inferior thing to do, much after it became computationally feasible, almost instantaneous, to estimate a logit model or a probit model with frequentist techniques. And there's lots of other things out there that fall in that same category. You had to make, more restrictive assumptions in order to get the computer to estimate, the model than you would like to make for substantive reasons. But, time goes on where everybody's estimating these more restrictive models for computational reasons, and then it becomes the way And if you try to do something that deviates from the way, then you have to explain that in your journal articles. There's been lots of other papers that did things the wrong way, so it's kind of easier to go with the flow than to do things the right way. And then it gets put in textbooks, and that's the only thing that people learn, and it just sort of persists on itself well past the time where it was computationally necessary. So to sort of think about this in terms of social science terms, like what theory in any branch of the social sciences would be dismissed if it was found, empirical evidence, let's say solid empirical evidence, that showed the relationship between, the key predictor that you're trying to analyze and the outcome variable was nonlinear rather than linear. So take, for example, like classic microeconometrics things such as, log wages is the outcome and years of schooling is the variable that you're trying to estimate the effect of. You could do some complicated thing like instrumental variables, but, don't worry too much about that. Suppose it was found that, the relationship between the log of wages and years of schooling, it was positive, but it was not constant. So, going to college or having 4 years of college gives you more increase in your log wages than going through 4 years of high school. Now, economists have been estimating that model using linearity assumptions for decades. But if it was found that there was some sort of accelerating relationship between years of schooling and, log wages, no one would reject the theory just because it wasn't a linear relationship. Because the people, economic theorists who were specifying are theorizing about models like this never said it was linear in the first place. There's no particular reason to think that would be the case, that the return to graduating from fourth grade would be the same as the return from, completing your senior year of college or your first year of graduate school in a master's program or something like that. So it's, when the direction of the effect is like negative, then, or, when you theorize something to be sort of an increasing relationship and the empirical evidence shows that it's actually a negative relationship, then that is pretty decisive evidence against the theory. But if the theory, didn't really specify that it was linear in the first place, and rarely do they do, but you as an applied empirical estimator come along and add that linearity assumption when you go to estimate the thing. If that's false, that doesn't really constitute evidence against the theory that never said the relationship would be linear in the first place. And so it's very difficult to come up with examples in the social sciences where having a linear relationship between, this and that is a necessary part of the theory. If there was a strong nonlinear relationship, then the theory would be considered wrong. Has anybody encountered an example where sort of the linearity is a substantive part of the theory? Any branch of the social sciences or public health or whatever other programs are represented here. No examples. One example.
There's this example of I can't really remember exactly, but I think it has to do with number of parties in a. But basically, it's
the number of parties and the proportion of turnout or something like that.
Yeah, it's a law. It's not the G, I don't remember exactly, but predicts that it's like 45-degree light.
Oh, the vote seats relationship.
Yeah.
Well, that's actually, yes. So that's not an empirical prediction, but if you have sort of pure proportional representation with no like amendments or anything like that, then the proportion of seats that a party earns is going to be exactly equal to the proportion of votes that that party receives. So that's not really an empirical prediction, but it is sort of a consequence of that sort of voting rule. However, in virtually all countries, you don't see it line up on the 45-degree line. You see like one of these things because the Constitution says, well, you have to have 10% before you get any seats or, you know, other things like that. It's not pure proportional representation, but we have districts that are gerrymandered and things like that. So I don't know that that exactly counts, but it's probably the closest thing that I can think of to where, so in that case, linearity is more like a baseline rather than something that anyone was actually theorizing. But in any event, all comparative political scientists recognize the fact that in most countries, that relationship isn't linear. It has one of these bow-shaped sort of things. So we're at, you know, somewhere between 0 and 1 examples where linearity is a substantive assumption of the theoretical model. So another example? Yeah. So can you think of an example you've seen in the political science literature where in the empirical section of the paper or the book, they estimated something other than a linear or a generalized linear model? No examples of that either. So we have approximately 0 theories that substantively require linearity and approximately 0 empirical papers that estimate anything other than a linear model. That's not good, but nor is it necessary. Back in the day, it was kind of necessary because, you know, generalized linear models have likelihood functions that are concave in the parameters. I could have written beta there, you know, the coefficient. So it's a concave function of all of those, and concave functions are easy to maximize. They'll have a single global maximum. You can get to it pretty reliably, but that presupposes that finding the mode of the likelihood is a good idea. At best, the mode of the likelihood is an approximation to the mode of the posterior distribution. But we know that the mode of the posterior distribution is a much inferior quantity to the expectation or the median or, you know, some quantile that you're particularly interested in, because the mode is only optimal if your loss function for a point estimate is binary, such that you're happy if you get it exactly right, and you're equally unhappy no matter how wrong your point estimate is. So seeking a mode is not really, even if it's, you know, easy to do, even if it was the only thing that was possible to do, you know, 40 years ago or something like that, it's not a particularly good thing to seek, whether you're estimating a linear model or a nonlinear model. But under the Bayesian approach, where we use MCMC rather than optimization, well, we don't really care about the mode anyway, nor do we, you know, find it in a lot of models, such as the hierarchical model that we were talking about last week. The mode has this weird property that, you know, the posterior density by definition is highest at the mode, but the probability of getting a draw that's close to the mode might be very, 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 very small. Which is to say, another way of saying that is that the mode posterior mode may not be in the typical set, and draws from the typical set are really what govern our estimation of these expectations or medians and things like that. But if we're not doing optimization, then the fact that linear models are easy to find the optimum of is not particularly relevant. We're still just going to be drawing from the posterior distribution in proportion to the probability of being in any small interval. But nonlinearity can make it more difficult to do Bayesian methods. So they really mess you up if you were trying to do a Gibbs sampler, because you're not going to be able to derive the full conditional distribution of the parameters you were trying to estimate. And there was a good 20 years where almost all empirical, papers and stuff using Bayesian techniques had to use Gibbs samplers. Metropolis Hastings was never really cut out for estimating models that are complicated like this. So this can actually be more difficult for NUTS, which is the algorithm implemented in STAN. It doesn't mean it's impossible. It just means there's more things to worry about than the rather limited number of things that we've worried about so far. But you can certainly estimate models, and you should estimate models where the relationship between the outcome and the predictors has various nonlinear forms. It's just going to be harder for STAN to draw from that posterior distribution efficiently than in a simpler model, even a hierarchical model sometimes. Yes?
I have sort of a naive question coming from the public company.
Okay.
So are linear probability models frequently used in social science? Because prior to QMS, of course, we never heard about.
They are still sort of used in economics. I think almost everybody else has moved on from them. I mean, they're like the diapers of probability models. But yeah, you still occasionally see it in economics, mostly because it's easier to interpret the coefficients. But if it's not the right model, then why even bother interpreting the coefficients? So it's rarer than it used to be, but yeah, it still happens.
So in the definition of what is linear and what is nonlinear, the definition that I'm aware of is that it should be nonlinear in the x's.
Or in the parameters, yeah. So like a logit model is considered generalized linear rather than linear. The reason why it's called generalized linear is the relationship between eta and x is linear. The relationship between eta and the probability of success, that's nonlinear. It has that logistic CDF transformation to it. But what we're talking about, especially here with nonlinear models, are ones where the relationship between eta and x is nonlinear, or eta and one of the parameters that generates eta is nonlinear. So we'll see examples of this, but you won't see many examples of this in the literature because those models would be a lot harder to estimate.
But isn't that like just saying it's polynomial regression or something?
So if you do a fixed, so yes, if you think about the relationship between y and x, that could be a nonlinear relationship. But if you put the logarithm of x into OLS, then it's a linear relationship between the log of y and x. So if you had something like, the model is related to the hyperbolic cotangent of x, that would be a nonlinear model.
Okay, because I thought like any log or exponential.
Yeah, but if
added into like nonlinear terms, like Taylor series or whatever.
It could, but that's not how those models are estimated. For any sort of fixed transformation, that's considered a linear model in the transformed variables. All right. Okay, so one class of models that you actually may have seen before if you took data mining. It's called generalized additive models, where the likelihood function for the sample can be written, I should have put y in there as well, as the sum of the squared residuals. So you have some, or proportional, there should be a -1.5 out here. But the relationship between y and x is governed by this unknown function s, which is going to be stand for a smoothing spline. And there's different ways of approaching these generalized additive models. They were sort of first popularized in the data mining literature, where you would sort of break your data up into training and testing, and then choose the value of the smoothing parameter in order to fit the data or the outcome best in the testing data. The Bayesian approach to this is to say, well, whatever parameters go into that nonlinear function, such as a smoothing spline, will have priors on them, such that, for particular special cases, you get back a linear function. And these splines, it turns out, can be written as the sum of some common linear function plus an observation-specific deviation from that linear function. So if xi is like above the mean by 2 units or whatever, we're going to have a specific deviation from that common linear function that kicks in at 2 values above the mean, et cetera. And it turns out that this amounts to writing eta with some centering and retransformation various rules as x beta plus z times b for a particular choice of the zi's. And so that puts it in the same form as the linear models estimated by the LME4 package. But then you can get the estimates and do nonlinear transformations of them back to put it in this form of y is predicted by some unknown function s, and then estimate what sort of shape that s function takes. So an example of how to do that with the stan_gam4 function in the rstanarm package. Here I'm using a data set in the mass package that I think I've used before in this class, trying to predict low birth weight births. So there's a few variables in here. Race is a factor. It should be a factor. Whether the mother smokes during pregnancy is the primary variable of interest. The outcome here is binary: 1 if the baby is born with low birth weight, 0 if the baby is born with normal birth weight. And I'm going to use this S function to say that the relationship between eta and age could have this general nonlinear form that's governed by a spline. The family is binomial because this special case is Bernoulli, particularly with models like these, but really with any model where you don't have informative priors. And it's hard to specify informative priors on how the sort of weights in a nonlinear spline function would work. It's good to specify the QR equal true option. It's also good practice to get in the habit of passing a seed to any model that's being estimated by Stan, so that your results are deterministic and you get the same thing every time you estimate the model. So when I estimate this particular model, I get a warning that says there are 2 divergent transitions after warm-up, increasing adapt delta above, this part got cut off, but increasing adapt delta above 0.95 may help and then it refers you to a link on the Stan webpage that explains what this warning means in more detail. It also says I might want to examine the pairs plot to diagnose sampling problems. So what does that all mean? We're going to come back to that in a second. But if we sort of ignore those warnings, which we should not do, we get results that look like this. So, we have estimates, for the intercept, different race categories. The smoking dummy variable has a point estimate of 1.13 with a standard deviation that's much smaller than that. So more evidence that smoking is not healthy for babies. And we see this S of age thing, which is basically kind of cut up the age range in the data and estimated a coefficient for each bucket of that. But there's actually a smooth relationship among the ages. So these sort of 9 coefficients that we get on the age variable are not easy to interpret. They do sort of suggest that it sort of starts out maybe a little bit positive and then it gets more negative. But as with everything, if you're not estimating just a plain linear model, no link function, Gaussian errors, you don't want to be interpreting these coefficients. You want to look at some sort of plot that shows the relationship. And you can do this on your own, but there's actually a plot underscore nonlinear function in rStanArm that you can call after you've estimated a model with Stan underscore GAM4. This is all very similar to the functionality in the GAM4 package, which was written by a guy named Simon Wood, who also wrote the MGCV package for R, which has been sort of a core R package. It comes with R for many, many years. Those of you who took data mining last semester might have remembered that I pointed out that there was really 2 packages that estimate generalized additive models: the GAM package by Hasty and other people at Stanford, and the MGCV package. And if you load them both, then nothing works. So I think we focused on the GAM package last semester. This semester, obviously we're focusing on rStanArm, but the syntax of that takes from the MGCV and the GAM4 package rather than the GAM package. But all of these packages have similar functionality, assuming you don't load them both, and then they have 0 functionality. But this plot nonlinear is a specific function to rStanArm for when you estimate a model following GAM4. And so we can see here the posterior median. So what we have on the vertical axis here is our estimate of the unknown function of age. So the relationship between age, which is the predictor in question here, and eta. In general, this could be a nonlinear function. And one of the things that we want to assess is it actually nonlinear? So what we see here, the posterior distribution of this nonlinear function actually turns out to be pretty linear. Maybe at like 30, it starts to decrease at a faster rate. But it was sort of already a decreasing function from like teenager up to 30. It just maybe becomes kind of accelerating down a little bit after that. But you can see in this data set, which is not very big in the first place, you have considerable uncertainty as to what the unknown function is when there are not that many data points with which to estimate it. So the dark blue line is the posterior median, median of the unknown function S. The light blue ribbon represents probably a 90% credible interval around that function. And, particularly for births where the age of the woman was greater than 30, we have a lot of uncertainty as to what the relationship between age and eta is. So I think this data set was sort of not intended to be representative. Certainly you could get bigger data sets where there were more births to mothers in their 30s, and you'd be able to estimate this nonlinear relationship more precisely, and you might very well conclude that it is pretty much linear. You would not want to really make a whole lot of inferences out, to 45 or something like that, where we have very few data points. But you needed to estimate a model that allowed the relationship between age and eta to be nonlinear in order to come to the conclusion that it actually pretty much is linear. And we're pretty sure that it's pretty linear for women who give birth in their 20s or even their late teens, because there are more observations here, and consequently the 90% intervals or whatever this is are much narrower than out past 40.
What was S again?
S is the unknown function that we are attempting to estimate. So it's basically saying the eta of this logit model is estimated with some smooth function of age, but not requiring that function to be linear, not requiring it to be increasing or decreasing, sort of a general function. Now it is making the assumption that that relationship is smooth. So it should not, it's assumed to not be the case that there's a discontinuity where, as soon as you turn 30, the relationship between, low birth weight and age is different than when you were, 29 and 364 days. So biologically speaking, that would be weird if that were the case. And so we're assuming it not to be the case. So you can have, increasing, decreasing functions. You can even have periodic functions, all sorts of things, as long as the function is sufficiently smooth. Basically, all of these are going to have at least 3 derivatives, of smoothness to them. And this relationship, we assumed it was smooth. We didn't assume it was linear, and we didn't arrive at a lot of evidence in the posterior distribution that it was not linear. But, if it had been the other way around, that low birth weight babies are increasingly common as the mother gets older and older, I don't think that would have contradicted any theory of anyone's, because no one was really saying strongly that there should be a linear relationship. It just kind of turns out to mostly be the case, as far as we can tell, conditioning on these data and only these data, which are fairly limited. Questions about that?
So each line horizontal is conditioned on SH or something?
S age is the posterior distribution of S age is on the vertical here. On the horizontal axis, we have age. And so it's saying the relationship between age and S of age is pretty much linear. And the relationship between S of age and eta is assumed to be linear.
Eta is the low birth weight.
Right. So the sum of the coefficient on the smoking variable, the race variables, and and then that is put into the inverse logit function to get the probability of a low birth weight baby.
Why is S not over all three? And just over?
Well, it doesn't make sense to have a nonlinear function of a dummy variable because it can only be evaluated at 2 points. So that would not be a continuous function. Certainly, at least not in our ability to measure race. You could conceivably have a continuous measure of how much the person smokes, like how many cigarettes per day or something like that. But in this case, like a lot of cases, it was just like, did you smoke when you were pregnant or not? So smoking is a dummy variable here. So all of these, you need a continuous function to really estimate a nonlinear relationship. Otherwise, you're just shifting the intercept of age or intercept of eta up and down. Yes. With the GAM function and the GAM package, yes. With the Stan GAM4, it's basically estimating the degree of smoothness. Implicitly, there's a prior on how smooth this is, but it's sort of a weakly informative prior. And so, no, for these splines, you actually don't have to put in a number of knots. These are what's known as thin plate splines. You can look that up on Wikipedia. But it doesn't have a number of knots, no. Questions? Okay. So I told you about the divergent transitions. There were 2 of them. This means for 2 iterations after the warm-up period, the numerical error in solving the Hamiltonian equations and all that accumulated for some 2 iterations, and thus the proposal for where theta would be in this space went off to infinity, or at least triggered the threshold in the Stan algorithm for saying, like, it looks like theta is gone. You remember when we first were talking about HMC and we, put up that curved surface and it sort of showed how it oscillated back and forth. You can sort of imagine, let's say you have some posterior that looks kind of like this when it's multiplied by -1, that you sort of start to move around and move around and move around. And eventually the numerical error gets like so big that you just sort of fly off the surface. So it's like a spaceship or whatever that, gets sufficiently outside the Earth's gravity that it just goes and it's not coming back. In that case, Stan stops the iteration or stops the Hamiltonian process for that iteration and just declares, this is a divergent transition. We did not calculate this stuff accurately and we lost track of theta. That's not good. But if the posterior distribution were anything close to multivariate normal, this wouldn't happen. So Stan should have no trouble at all with something that's multivariate normal or anything vaguely multivariate normal. So when you see these divergent transitions that your posterior distribution is pretty far from this sort of nice, regular, multivariate normal shape. And always keep in mind that the posterior distribution is multivariate normal under the same asymptotic conditions that the sampling distribution of the maximum likelihood estimate is multivariate normal. So if Stan is having trouble, if it's going slow, if it has divergent transitions, if it has numerical exceptions being thrown, etc., those are all indications that the posterior distribution is not, well shaped like a multivariate normal. And there's not that there's anything wrong with that. Like, that is legitimately the posterior distribution conditioned on these data. But what a lot of people do, so they're kind of first trying Stan, they run into one of these warning messages and they say, well, Stan is not working correctly. I'll just do something simpler like maximum likelihood estimation or something like that. But in the situations in which Stan is giving you these warning messages, it's basically saying your data are not numerous enough or not rich enough to yield a multivariate normal sampling distribution either. And so the asymptotic assumptions underlying maximum likelihood estimation are not being met either. It's not really a problem for Stan if you can do something about it to make the divergent transitions go away. And so the first thing that you should do is to try to increase the value of adapt delta. If this warning message hasn't gotten cut off, it would have said increasing adapt delta above 0.95 may help. And so adapt delta, it came up before. This is basically telling Stan, kind of in an indirect fashion, higher values of adapt delta are telling Stan to make smaller steps. And if Stan takes smaller steps, then it's going to have less accumulation of this numerical error, and you're less likely to have divergent transitions. So when you see this, really the first thing to do is to try to bump up the value of adapt delta. Now, when we get to doing things in Stan, the default value of adapt delta is 0.8. For the models that we've written in our Stan ARM, we found that that tends to be too low. So the default value in some functions in our Stan ARM is either 0.95. In some cases, like Stan _LM, it's 0.99. So we already bumped it up to try to eliminate as much as possible these divergent transitions. However, BRMS just continues with the Stan default of 0.08, 0.8, and that is often too small. If increasing adapt delta doesn't work or does not eliminate the divergent transitions, the next thing to try is to see if maybe there's more prior information that you have available than you're utilizing. So, oftentimes you might think, okay, this coefficient has like a normal prior with a mean of 0 and a standard deviation of like 3. But just to sort of be, inclusive of people in your audience who might have other ideas, I'm going to put in a prior of like normal 0 with a standard deviation of 10. But putting in priors that are, very weakly informative may yield posterior distributions that have long tails. Those are harder for Stan to deal with, more likely to get divergent transitions and things like that. So you might go back and see if the priors that you used were sort of less informative than what you really believe. And so increasing the strength of your priors that you specify to be closer to the priors that you actually believe will also often be able to diminish or eliminate these divergent transitions. And then if that doesn't work, the next thing to try is to re-parameterize your model. But to do that, you need to actually specify the model in the Stan language, which we will start to learn next week. All right. So the link that's given here has some more information about that, and that link will pop up whenever there are any divergent transitions in your chain. So the second thing that you might get a warning about, probably not so much if you use RStan ARM or BRM, is hitting the maximum tree depth. So what does that mean? So let's say you crank up adapt delta, and so the Stan is taking small step size when it does the no U-turn sampling. That implies for any finite number of leapfrog steps, this Hamiltonian trajectory process may not have started to U-turn by that number of leapfrog steps. And so Stan by default has a ceiling on the number of leapfrog steps that it can take per iteration of 10. So if you are using regular Stan and you have one of your iterations goes for 10 leapfrog steps but still hasn't hit the U-turn point, then it just sort of stops the Hamiltonian process for that iteration and chooses one of the footprints that it's been. But if you're hitting the ceiling, then you're not able to sort of fully explore the typical set of the posterior distribution on each iteration. So you want it to be the case that you can sort of get from any area in the typical set to any other area of the typical set in one iteration by doing some sequence of leapfrog steps. So if you find yourself hitting the maximum, then you need to bump the maximum up so we can go farther. Otherwise, you'll induce more dependence between consecutive draws because the second of those two draws won't have as much opportunity to get farther and farther away from where you started from on the previous iteration. Now, this is unlikely to happen with models in RStan-ARM or models in the BRMS package because the default for those increases the value of maximum tree depth. RStan-ARM uses 15. I believe BRMS uses 20. So you shouldn't often see that problem. But if you do, particularly with BRMS or with STAN, you need to specify, or any of these, specify the argument control, which is a list that takes a variety of tuning parameters, and you can specify max tree depth to some value greater than 10 so that you no longer encounter those warning messages.
So like, is it like it's stuck somewhere?
It's not stuck, it's just taking very small steps. And so it needs to take more steps than what you're allowing it to get all the way around the typical set of the posterior distribution.
Should we increase some subitration or something instead of trying to fill in this thing?
Fiddling with this shouldn't be a problem. It means it's going to run longer, but this is sort of a very good solution to the problem of hitting the ceiling on the tree depth is to make the ceiling bigger. You can pretty much always solve this problem whenever it comes up by increasing the maximum tree depth. Okay, so I'm going to flip over to ShinyStan. So I'm going to launch that. Go back to what we talked about before. So in the previous model that we did, there were no, like a few weeks ago when we were first learning ShinyStan, there were no divergent iterations. So there wasn't a whole lot to see here. But when there are, in addition to seeing the warning right after it finishes sampling, in big red letters here, ShinyStan will tell you that there are 2 divergent transitions. You might want to think or know where in the parameter space those divergent transitions happen, and those are conveniently indicated by the larger red points. So this is not the eyes of a blue ghost, but rather these are the 2 iterations that have divergent transitions, and you can look, in terms of another variable to see, if there's maybe something going on with that variable that, you're in. So that did not really help except move the eyes farther apart. Could it be related to this age thing? Maybe. So these sorts of shapes to the posterior distribution where it gets really narrow at something like 0 often lead to curvature that's too great and divergent transitions for any given value of adapt delta. So you can look through some of these plots to get more information as to where they're occurring. So that is not particularly helpful, but the divergent transitions occurred here and there. You can get, if there were more of them, then these other plots would be a little bit more helpful. you can click on HMC/nuts statistics and see more. So actually chain 2 and 3 didn't have any divergent transitions. Chain 1 and chain 4 had one each. But just because there's only one, that doesn't necessarily mean that it's not a big problem. Oftentimes, you'll increase the adapt delta a bit and your answers won't change that much, but it's good to go through that additional step just to make sure you're doing well. So this first plot, first couple of tabs here, those can be useful for getting more information about the kind of nature of the divergent transition. So always be using shiny stand.
What's the value of plotting the log posterior with respect to just a predictor?
Oftentimes you'll see divergent transitions either near the mode or near the tail. So it's good to look at the value of the posterior kernel in log units against the parameter that you're investigating to see, you know, what part of the posterior distribution Stan was having trouble with. But it's still just going to be kind of a one-dimensional slice of the posterior distribution. Most of these parts of the posterior distribution where Stan gets into trouble have to do with like weird multivariate shapes. So what we're going to see next is the so-called pairs plot, which can be brought up by calling the pairs function. You usually are going to want to specify some subset of the parameters because otherwise this plot can be so small that it's very hard to read. So here I'm going to look at all the variables except for the age variables. And so what we were looking at before was sort of a one-dimensional slice of the posterior distribution. Now we're looking at two-dimensional planes of the posterior distribution. So here, for example, is the bivariate distribution between the intercept and race 2, whatever that is. I think white were the baseline rate. So here we can see here between the intercept and smoking that there's a negative correlation in the distribution of our beliefs, between these two variables. And there's nothing wrong with that. But sometimes you'll see odd shapes that sort of have this funnel kind of structure to them, where for like part of the plane, there's like big variance in the posterior distribution. And for another part of the same plane, it gets really narrow, like the neck of a funnel. And you will often see divergent transitions when Stan kind of falls into the neck of that funnel as it's going around through the posterior distribution. So it's probably a little bit hard to see here because there's only two divergent transitions, but the divergent transitions will also be overplotted in red. In this case, they tend to come up by the mode. There's another thing about this pairs plot that a lot of people find confusing is, well, why doesn't it look sort of the same above the diagonal as it does below the diagonal? It's often roughly the same shape, but it's not like it's exactly a mirror image of each other, even though the sort of relationship between intercept and smoking over there ought to be the same as it is over here. The reason why we have an upper triangle and a lower triangle is the ones in the lower triangle, they basically have above median numerical error. And the ones above have below median numerical error on those iterations. And so what you'll often see is the divergent transitions popping up, and they're going to be overplotted in the lower triangle here, indicating that they're sort of a consequence of the inability to evaluate the posterior distribution, its gradient, its Hamiltonian equations, etc., with sufficient numerical precision in order to keep the error from accumulating and then eventually forcing a divergent transition. So you may sometimes see red points over here at the top right indicating divergent transitions even when there wasn't much numerical error. In that situation, increasing adapt delta almost always works. Increasing adapt delta when you have divergent transitions in the lower triangle sometimes works, sometimes doesn't. But it's worth giving it a try. If there were instances where we're hitting the maximum tree depth, those would be plotted in yellow. None of those happened in this particular situation, and they usually don't with our stand arm. Another message you may occasionally see, usually not from our stand arm, is that the Bayesian fraction of missing information was low. So what does that mean? If we define the total energy as the sum of the potential energy and the kinetic energy, both in log units, then we get the total energy. And if everything is going well, this total energy should be independent of the realization of theta for that iteration of MCMC. But if things are not going well, then you'll see, association between the energy and the position of theta. And in that case, the mixing through the posterior distribution will probably be very poor. And any finite number of samples is unlikely to give you a good estimate of the expectation or of whatever function you're interested in. So you probably won't get this warning very much from RStan arm. You may get it from BRMS or other functions that you do yourself using STAN. And that usually indicates you need to think about a different parameterization of your model. Because with this parameterization and this data, it really can't sample from the posterior distribution effectively because it has a sufficiently non-normal shape to it. Probably has really thin tails or something like that. So you may see that warning too. Anytime you get one of these warnings, there'll be a link where you can read more about it and it'll have more recommendations about what to do. But you will see some of these warnings as you get into more complicated models. However, sometimes the warning is merely a result of the starting values being weird. Those by default are randomly chosen. And sometimes the chain can just get off to a bad start. It makes it hard for the adaptation to go well. And if it gets a poor value of its adaptation parameters, then the post warm-up period where it's sampling from the posterior distribution can also perform poorly. So when this happens, another thing you might try is to set the init_r argument to some value less than 2. 2 is the default, but a lot of times that is too wide. What that means is that the initial parameters are drawn from a uniform distribution between -2 and 2. And so if you have a lot of parameters, some of them are going to be really close to 2, some of them are going to be really close to -2. That may be, so far away from the true parameter, if the true parameter is close to 0, that, Stan has trouble getting out of the gate on that. So 2 is really too big. But oftentimes it doesn't really hurt anything. But if you need to, you can make that smaller. You almost never need to make that bigger. But in some cases, you want to reduce that to 1 or 0.5 or 0.1 to get the starting values all closer to 0, particularly if you're estimating a big model or something like that. All right. So you can also do splines with BRM. So here I'm just calling get prior with the same formula as I was using before. It sort of tells you that there are improper priors on all these coefficients. It's estimating the standard deviation of something to have a student T, and it's going to be estimating the standard deviation for how much this nonlinear function of age wiggles around. So if you do this using VRM, by default, it's going to have an adaptive delta of 0.8, and you get something like 130 divergent transitions, which is way, way, way too many. And the reason why that is the case is we forgot to add the control argument for list adapt delta and make it some big number. If you set that to 0.99, you pretty much get the same thing as with RStan arm, maybe 1 or 2 divergent transitions. You could increase it up a little bit closer to 1 and probably get rid of all of those. The BRM doesn't have the option to use the QR reparameterization, and the QR reparameterization often helps to avoid divergent transitions. So here, you might actually be able to see the red points better because there's like 100 of them. This is the pairs plot as you pass it, the object is returned by VRM. So yeah, you can see red in the bottom triangle here, nothing as far as I can tell in the upper triangle. So this was a situation in which the default value of adapt delta was much too small for this posterior distribution, considering this posterior distribution has this nonlinear function of age that it's also trying to estimate. Okay, so you don't have to estimate splines, although splines are often a good choice. You can put in your own nonlinear functions, and these sometimes have something of a theoretical justification. So here we're doing an example with simulated data where y has a conditional mean that's some scale b1 multiplied by e raised to the power b2 times x. So we have an exp in here that gives us this nonlinear relationship. We can put priors on the nonlinear parameters b1 and b2 in a BRM model. The only thing that's a little bit different is we need to wrap the formula in this call to the BF function. And this is pretty much like a list. The first thing is you're sort of specifying how y is related to x through the antilog function. And then you need to specify how these parameters b1 and b2 are generated. In this case, I'm just saying, well, they're a function of the intercept each. But I could specify a more complicated model where b1 is a linear or maybe even a nonlinear function of some other variable z. So you can think about these parameters in a Bayesian model as having their own functional forms. In this case, I'm just saying they have an intercept form, but I could have done something more complicated than that. I can summarize the results, and so now it's telling me the value of the posterior means of b1 and b2. I might want to plot that relationship. Actually, I do want to plot that relationship using the plot wrapped around marginal effects, specifying points equal true to put the circles on here. And so here we can see the smooth function that we were estimating. It's constrained in this case to be an exponential function, but the shift to it and the way it accelerates is estimated to be a function of the b1 and the b2 parameters that we're getting the posterior distribution of. And in this case, if you have a reasonable amount of data and you specify a particular functional form, you can estimate that functional form with a high degree of precision. So this ribbon for the 90% intervals is really like very, very small until you get into the region where there's less data. And then it gets bigger, but it's still a lot smaller than the tail when we were estimating the effective age on low birth weight. So there are some theories in the social sciences or whatever where people will specify as part of their theory a particular nonlinear form. That's actually more common than a substantive person specifying a linear form. And so you can estimate those or any other nonlinear relationship you want relating, eta to x. So
This is a linear model, so if we take the log of the other side, it's just b1 plus b2x.
yes, it is a linear model in the logarithms,
Right.
but we're estimating not with the logarithm, just with the regular y, in which case it's a nonlinear model.
So we could just if we just did linear, if we just did log of both sides and we did it, would work as well.
Yes, you would get the same posterior distribution of beta 1 and beta 2. But, you could, let's say instead of EXP, it was square root or something like that. Then it would no longer be something that you could just do with logarithms. Okay, so we got that. There's a final example. This is also taken from the BRMS vignette. Someone was estimating an insurance model, so the cumulative loss of the insurance company as a function of these things, some of which you had data on, some of which you didn't. Another, and some parameters to estimate, another thing that you want to keep in mind when estimating any model, particularly complicated models, is to scale the outcome variables so it has reasonable units. So the original units here for cumulative loss were in dollars. And that gives rise to a posterior distribution where, these parameters have like huge numbers for their posterior means and medians and things like that. That's harder for Stan to deal with. So what I did here was just divided the outcome variable by 1,000. So now it's in units of thousands of dollars of loss. Could have even done like millions probably if this is a big insurance company. And doing so yields a posterior distribution on the unknowns like volt and theta and omega that is like closer to zero, but not so close to zero that Stan has problems with it being too close to zero. Paul did have to specify a gap delta of 0.9 in order to get rid of the divergences in this model. But you can see the nonlinear effect here of dev, whatever that means, on cumulative losses. Now the units are in thousands of dollars. So we see sort of a relationship like this, certainly with considerable uncertainty as we get out here. But also we see our model might be missing a sort of shallower curve. It could be, omitting a variable that sort of shifts the whole thing down. And so looking at these plots can help you understand where your model is not doing so good. Okay, actual final thing for today, since we're gonna have homework, the last slide has some knitter tips for how you wanna do things in Stan. When you're actually estimating the model, like drawing from the posterior distribution, it's good to specify a label for the chunk so you can refer back to it. Cache equal true. That means if you re-estimate the model but you don't change anything, it doesn't take the time to actually draw from that posterior distribution again. It just pulls up the saved results. Also, results equal high will not print out all the progress and stuff of Stan into your HTML file. So just kind of make a chunk that has these options, and then you call Stan LM or Stan GLM, whatever it is, and then make another chunk where you print out the output or you make plots, and that can have regular options to it. It's also a good idea to pass the seed argument so your results are deterministic. And if your computer has multiple cores, which most computers do these days, you can specify the mc.cores option and things will run faster because it will use as many cores as are available, one per chain. So you can get things to go a lot faster. But definitely remember this cache equal true. If you change some of the options, it'll re-estimate the model. But if you just leave everything the same and knit it again, then it will use the cached version of that, which is saved on your hard disk, rather than recompiling and re-estimating the model again and again. All right? Okay, so go to Rob's talk tonight. Go to the review session tomorrow. I'll post a new homework, and we'll start talking about how the Stan language works next week.